Hello everybody, my name is Mohamed RGUITI. I am Associate Professor at the Laboratory of Ceramic Materials and Associated Processes at the Polytechnic University of Hauts-de-France. My talk is entitled Electromechanical Performance Prediction of PiezoPLA films for Energy Harvesting, Sensing and Transduction. As a partner in this project, our task is to characterize macroscopic piezoelectric properties of PLA and verify the potential of this material for energy harvesting depending on the processing conditions. Some tests have been carried out in this work to verify the feasibility of these materials to be used as sensors and in ultrasonic transduction. Then I'm going to talk about how the piezoelectric constant of PLA was determined. Then I will show you some results about energy harvesting using mono-oriented PLA films. Then a model is proposed to get the impact of various parameters on the piezoelectric properties. And then some tests will be presented about sensing and transduction applications. And I will finish with some conclusions and perspectives. As presented in previous presentation, PLA has a spontaneous shear piezoelectricity without pulling. To measure this piezoelectricity, a shear stress is then needed and must be applied in the stretching direction of the initial extruded film. However, in the laboratory, a tensile stress is easier to apply than shear stress. For that, the initial extruded films were metallized by silver electrode and then were cut at 45 degrees from the stretching direction. This direction cut permits to apply a maximum stress on the molecular chains. So rectangular samples are then used to measure piezoelectric properties and also for energy harvesting tests. For piezoelectric characterization, a BIOHARV is used. For that, two PLA films are glued together in series connection. One end of the BIOHARV is blocked and the other is free. When voltage is applied, one sheet elongates and the other contracts. So that led to a bending movement. The tide displacement is measured by a laser vibrometer. The transverse piezoelectric constant D31 is then calculated using this equation, which shows that D31 is related to the voltage, deflection, thickness, and the free length of cantilever. The shear piezoelectric constant, the 1,4, is twice D31. The piezoelectric measurement is first performed on a commercial PVDF film. Here is presented deflection of PVDF versus applied voltage at different frequencies. The slope of this line permits to calculate a value of 20 picometer per volt. which is close to that provided by the manufacturer. This procedure is therefore validated on PVDF. Thereafter, the same methodology are followed to measure G31 in PLA. Here is presented an example of PLA deflection regarding applied voltage. The G31 value obtained here is 3 picometer per volt. Measures are carried out on different PLA grades with different stretching ratio. We have observed a beneficial effect of stretching on piezoelectric properties. The maximum value obtained for our PLA is 6 picometer per volt, but in the literature, a maximum value of 20 picometer per volt is reported for PLA. For energy harvesting tests, the aim is to compare different PLA grades studied in this project and stretch it at different ratio. For that, rectangular films are cut at 45 degrees with these dimensions. One end of each film is blocked and the other is attached to a linear motor. This motor is controlled by a PC in terms of displacement and frequency. A different strain and frequency can be then applied. The generated voltage is measured by an oscilloscope, and for each kind of test, a comparison is made between PVDF and PLA. We can see here that recovered voltage depends on the frequency. Concerning voltage, here are presented results obtained for PVDF and PLA. We can see for the two materials that recovered voltage depends on strain and frequency. Also, this strain and frequency have a beneficial effect on the harvested voltage. And due to difference of piezoelectric properties, voltage harvested from PVDF is higher than voltage obtained from PLA. Regarding power, here are results obtained from voltages presented in previous slide. The power is calculated from voltages measured on film with this surface using the resistance load of the oscilloscope, 1 megaohm. We can see again that recovered power depends on strain and frequency and reach about 100 microwatt at 20 Hz for a strain of 1.5%. The same conclusions can be done for PLA about strain and frequency, and we can observe that power harvested from PVDF is about 100 times higher than power obtained from PLA. In order to understand the impact of various parameters on the piezoelectric properties, a model is developed from the standard form of the piezoelectric constitutive equations. For thin structures, the general equations can be simplified as presented here. From these equations, voltage and power can be calculated in function of different physical parameters of film. All these parameters necessary for the model have been experimentally determined. We can see here the comparison between theoretical and experimental results for PVDF at 20 Hz. On the left is presented harvested voltage according to this trend. The pink area corresponds to maximal estimated theoretical error. On the right, experimental and theoretical power are presented according to the load resistance. We can see that a maximum is obtained for an optimal resistance load, which depends on excitation frequency and electrical capacity of the film. These results show a good correlation between experimental and theoretical data. Here are presented the results obtained for PLA. The same conclusions can be given here with a relative error on the right, relative error for power more important between theoretical and experimental data. In this table is reported a comparison of maximum power of the different PLA grades and PVDF. We can observe that PVDF power is very high compared to PLA, and also the importance of load resistance value and measured power. This power can be improved by optimization of electronics and using a capacitor for energy storage, because many losses have been observed due to electrical wires. In this slide, we have tried to predict by model the influence of different parameters on piezoelectric response. Here are presented the estimated voltage and power if piezoelectric coefficient, dielectric constant, and Young modulus increase beyond actual values of PLA. These black points represent experimental values, and 20 picometer per volt represent the limit of piezoelectric coefficient of PLA reported in the literature. We can then see that the increase of these physical parameters have a beneficial effect on harvested voltage and power. These estimated values, estimated theoretical values, must be confirmed by experimental results, and for that it would be interesting to see how to increase these physical properties during film's elaboration. In order to demonstrate the ability of the PLA to be used in piezoelectric applications, some tests have been carried out. The first one is about impact sensor. For that, a steel ball is rolled inside a glass tube and falls on piezoelectric polymer. The impact produces an electrical signal by piezoelectric effect. Here are presented piezoelectric responses of PVDF and PLA films following this impact with a mechanical power of 4 watts. We can see here that the recovered electrical power by PVDF is only twice higher than power obtained by PLA. That demonstrates the potential of PLA films for impact sensing applications. A preliminary ultrasonic test was also done to evaluate the ability of these materials to generate and receive ultrasonic waves. For that, an electrical signal excites a first PLA film or fabric used as emitter. The generated ultrasonic wave propagates in an aluminum plate and received by another PLA film or fabric, PLA fabric, used as receiver. So no ultrasonic behavior is observed using PLA films in these tests. However, a good ultrasonic behavior is obtained by a PLA fabric at two different frequencies, at 45 kHz on the left and at 9 MHz on the right. That demonstrates a very promising results. It's necessary to make more tests to confirm these results. If we resume the results obtained on variation of voltage versus strain and stress, we can suppose that strain and stress sensors are possible with these materials. For that, an electronic packaging is necessary to carry out these kinds of sensors. To conclude, a beneficial effect of stretching of piezoelectric properties is observed. A good correlation is obtained between theoretical and experimental data for voltage and power. Some potential applications with PLA are demonstrated, and the establishment of an electronic circuit is needed to improve harvested energy from these materials. Thank you very much.